All right, everyone, let's get started. Today we're going to do some proofs and pigeonhole principle and a proof by contradiction. So let's just jump into the first question. It's about a sequence problem where you're given a sequence recursively by a sub k equals to 2, a sub k minus 1, and minus 3 for k is greater or equal to 2. And then you're given your a sub 1 is 4, which side you wanted to prove that the one that the closed formula, it is true given the recursive one. So I'll just give you guys about 3 minutes to work on the first two, the part A and part B. So anyone who wants to talk about what you get for the first four terms?
I got 4, 5, 7, 11, and 19 for both of them.
Mm-hmm. So we're just going to verify the recursive formula and the closed formula for the first four terms. Where you should get the same for the closed one. Okay, all right, and the part B is that we want to write out the R8 and R9, basically just by substitution. Anyone wants to shout it out? What is R8 R8?
131 is what I got.
Mm-hmm. And what about R9?
259.
Okay, 259. All right, and let's move on to part C. So suppose that Amanda has already verified R8, which in this case would be, I'm just going to write it here, R8 is equal to 131, and show how to verify R9 without starting all over. I'll give you guys 1 minute to work on this. All right, is there anyone who wants to share the thought process? How would you verify R9 given R8 has already been verified?
Well, I think you just use the recursive formula and plug in the result of a sub 8.
Yep, exactly. So we want to start with the recursive formula. If we just plug that in, and since we already verified A8 is the same as R8, so we can just replace that with R8. And we know R8 is 2 to the A minus 1 plus 3 and minus 3. And if you just rearrange this, you would get 2 to the 8 and plus 3. And that is the same as 2 to the 9 minus 1 plus 3, which equals to R9. All right, any question on this one? Okay, so let's move on to the next question. It is still another sequence problem. So for this one, we're also given a recursive formula, and we just want to show that it is equivalently described by the closed formula, except n equals to 2 to the n minus 1 plus 3, and we want to use the induction. So remember the 4 steps, which is problem statement, and we have base case and hypothesis and the deductive steps. And I will give you guys about 3 or 4 minutes to work on this problem. All right, so let's just jump to the base case. We want to show that the first term in these two formulas are equal. So we're given that the recursive one is a1 equals to 4. And we just need to verify when n equals to 1. The closed formula a1 is still equals to 4. So we have proved that base case is true. And what's going to be our hypothesis? Anyone wants to share like which term you pick? Like the hypothesis can be we can assume that Pn is true, and we want to prove that P of n plus 1 is true. Or you can assume that P of n minus 1 is true and show that P of n is true.
I think that assuming P of n and then proving n plus 1 is true is easier in this case.
Okay. Let's just assume that. So I want to assume that P of n is true. And the Pn in this case would just be, we assume that A sub k is equivalently described by A sub n. Or I would rather write in the form as well, let me so is that equals to the n minus 1 plus 3. Okay. And how are you going to start our inductive steps?
Then we have to state that we're going to show that's a to the n plus 1 is equal to the n plus 1th form of the recursive formula.
So we can start with A sub k plus 1. And just by directly looking at the formula defined by the, just look at the recursive one. So A sub k plus 1 would just be 2 times A sub k minus 3. And what's going to be the next step going to do?
Use your inductive hypothesis and plug in AK is equal to 2 raised to n minus 1 plus 3.
Yep, exactly. And that's all come from the hypothesis. And then in the end, you should get, oops. Is 2 to the n and plus 6 minus 3. And this is 2 to the n plus 3. Which it is the form of A sub n plus 1. So you can see that A sub k plus 1 is equal to A sub n plus 1. And thus you had proved that P of n plus 1 is true based on P of n is true. All right, any question on this one? About how we use induction to show their equivalent? All right, so the next one's going to be the pigeonhole principle. So we want to use the pigeonhole principle to prove that given any 5 integers, there will be 2 that have a sum or difference divisible by 7. So a pigeonhole principle is that if m times n plus 1 objects are distributed among n containers, then there must be some container containing at least n plus 1 objects. So if you have m times n plus 1 that's like your total objects. And then you want to distribute it among n containers, like or n boxes. There must be some container that containing at least n+1 objects. So just think about this number and what's going to be m and n in this problem. And I'll just give you guys about 3 or 4 minutes to work on this one. It's always more intuitive if you can draw some little boxes to represent your containers. And then just mark each of them to show that what are going to be the numbers in it, in which you're going to use proof by cases. All right, so how many containers should we have in this problem?
Four.
And do you want to talk about like how did you get that?
Yeah, so I start usually with objects. So I know I'm going to have 5 objects because they said given any 5 integers. And then objects in the container that they would like is 2. So there will be 2 that have, that's what indicated it. So it's m plus 1 is equal to 2. So I have m is equal to 1. And then using the equation mn plus 1 is equal to 5. Well, m is 1, so n should be equal to 4.
Yep, exactly. That's exactly the way you're gonna find like how many containers you need in this problem. So you just need 4. And then how would you arrange how would you assign the integers of the form? 7k or whatever.
I
Put
use
in-
the division theorem to determine the remainders. So I have my boxes with one of which is r equals 0, r is equal to 1 or 6, r is equal to 2 or 5, and r is equal to 3 or 4.
Yep, that's perfectly how you're gonna do it. I just labeled this containers as 1, 2, 3, and 4. So right here, the r is just the remainder. This was just the same as 7k. And for the second container, which is be the integer gonna have the form like 7k plus 1 or 7k plus 6, and similar for container 3 and 4. And then how would you gonna do next to use proof by cases to show that there will be 2 that have a sum or difference divisible by 7? So what's gonna be our next step?
I did 2 cases. The first case I did is if it was like the same remainder, and the second case is if it's opposite remainders.
Yep, you could. There's another way is that for each container, you can have like a specific cases, but essentially it's all the same. So you can just have like 2 like larger cases, like as you said. So the case 1 would just be if they both have the same remainder when divided by 7. So in this case, if I just use let's see, that the first two integers are going to be 7 with the form of 7k plus r, and the second one is also 7k plus r, since they have the same remainder. And if they have the same remainder, you can use the fact that the difference would be this, and which you end up with 7k plus r, sorry. So which would just give you 0. And we know that 0 is divisible by 7.
On this one, wouldn't you, for that second k, wouldn't you use a different variable like maybe m?
Oh, you mean right here?
Yeah.
Yeah, you should. sorry about that. Yeah, you wanna, because they're not necessarily like pointing to the same number, so they can be like different numbers. You just have like the same remainder. And the second case, or the second larger case, would be if they have different remainder, but since they're in the same box, since they're in the same container, we know that the R1 plus R2 will equal to 7. And that's because they're in the same container. And this time you can use the sum of the two numbers to check if the result is divisible by 7. And that's just 7 Q by closure. And then you have proved that the two have like a sum or difference divisible by 7 with these two cases. Any question on the pigeonhole principle? Great. Let's just move on to the next one. So the next one's going to be proved by contrapositive. So the first thing I'm going to do, just write out the contrapositive of this statement first. So remember that if you have like implication where P implies Q, what's going to be the contrapositive?
Not Q, not P. Not Q to not P.
Yep. So not Q implies not P. All right, I will give guys about 2 minutes to work on this problem. All right, so anyone wants to say about what's the contrapositive for the of this statement?
Contrapositive would be there exists real numbers x and y. If x squared plus y squared equals 0, then x equals 0 and y equals 0.
Okay, so I think somehow you're talking about the contradiction, but not exactly the contrapositive.
I would reword that to just say if x equals 0 and y equals 0, then x squared plus y squared equals 0.
Yep. And you won't change the first half sentence. It's still going to be for all real numbers x and y. If x equals 0 and y equals 0, then x squared plus y squared equals to 0. And that will be your contrapositive, and which is the statement you want to prove. And this one should be fairly simple. How are you gonna start the proof?
I think you just get to substitute x and y in and just kind of reflexively equal 0.
Yep, and another the way I'm working it, just write it like left-hand side, it just equal to if I just substitute that x equals to 0 and y equals to 0, and x squared plus y squared becomes 0 squared plus 0 squared, and that's 0. And the right-hand side would just be 0. And then you can say, okay, 0 is equal to 0, so we have the left-hand side is equal to right-hand side. And then you can say, thus, since the contrapositive of the statement is true, the logically equivalent original statement is true as well. All right. Let's move on to another induction problem. So which right here you have a summation, and then you want to show that these two formulas are equivalent for each n is greater or equal to 1. And again, for the key part for the induction would just be making sure what's going to be your hypothesis and what is your inductive steps. So I'll give you guys about 3 minutes to work on this one. All right, so for the base case, we can just substitute that where when our n equals to 1. And this is just going to be 1. And for the right-hand side, it would just be 2 to the 1 plus 1 and minus 1 minus 2. And that's still 1. So we have proved the base case. So what is our hypothesis in this case? Or which one do you choose to assume it, or which term do you choose to assume is true?
I think the sum side would be easier. Oh, sorry. You mean weak or strong? How about m minus 1 just for variety?
Yeah, we can assume that n minus 1 is true. So in this case, it would become 2 to the n and minus n, and that's plus 1 and minus 2, and that's minus 1. Yep. And then for the inductive steps, what are you going to do next? So where do you going to start?
Excuse me, just hold on for a second. The original n formula is that 2 to the n plus 1 minus n minus 2, right? If minus 1, if n minus 1, so it should be 2 to the n minus 1 plus 1 and minus n minus 1 minus 2 should be minus 3.
So yeah, but we're substituting that n equal n minus 1 here. So if you take out the parentheses, that would be plus 1.
Oh, okay, my bad.
Yeah, so you have minus 1 and plus 1 and minus 2. And that will give you minus and minus 1.
Yep, thank you.
So we can start from the left-hand side where we want to show that we're trying to show that P of n is true, since we assume that P of n minus 1 is true. So we're starting from here. And how would you utilize the fact that the previous term is true in the hypothesis? Or in other words, how would you create this?
Can we expand out the sum and then replace everything up to 2n minus 1 with the other formula, with the closed formula?
Yes, and that's exactly what we're going to do. So we can rewrite this starting from 1 and all the way goes up to n the summation. Just rewrite this as starting from I equals to 1 and all the way up to n minus 1. And then plus 2 to the n minus 1. Okay, everybody agrees on this step?
Where did you get the 2 to the n minus 1?
So the 2 to the n minus 1 is just the last term of the summation right here on the left-hand side. So the last term of the summation, where you start from I equals to 1 all the way up to n, you just basically substitute the when I is equal to n.
Okay, I see.
Yep. And then you can just replace this this term with the closed formula, which is 2 to the n minus n and minus 1. And then you plus the last term. And then you just rearrange this. That should give you minus n and minus 2. And that's actually exactly the one we want. And this should equals to, just trying to rewrite this as minus n plus 1 and minus 1. Wait, I think I just left a term. Yeah, so right here would be minus, oh, never mind. My bad. Sorry. I'm thinking about like the n plus 1 term. So it just should be in this form. This would be your final answer. And that's exactly the two equations you have here, which is you just show that P of n is true. All right, and you can also you can also assume that P of n is true and show that P of n plus 1 is true. Any questions on this one? All right, so let me just stop here, and if anyone has like any other questions, you can stay and ask, and otherwise you're free to go.
Thank you.
Thank you.
Have a nice day.
I
Thank
do
you.
have a question.
Yeah, go ahead.
On the induction step, if we were to have done n plus 1 instead of n minus 1, what would that 2n minus 1 on the right hand side have turned into?
If you're gonna assume that n plus 1 is true, and then you want to show that n plus 2 is true,
Yes.
which side are you talking about?
The right hand side of the induction step where you did the 2n minus 1. What would that be instead? Because there's a similar problem on the homework that I'm having trouble with, so I'm just curious.
So let me see. If we assume that n plus 1 is true, let me just write this out. So this will just be, you're just gonna substitute the n plus 1. So that, yeah. All right, and this will be your hypothesis. And for the inductive steps, it's just like all the similar steps where you're gonna leave out the last term and then just have all the previous term. And the last term will just be 2 to the n plus 2 minus 1. And then you're just gonna substitute this part, yeah, with this.
Okay, that makes sense.
Mm-hmm.